Recording started.
All right, hi, welcome back, Chem 30 students. This will be part 2 of the electrochemistry session, and we will start things off by looking a little bit more in depth at some problems that involve assigning oxidation numbers. And so we're going to start with this one here. We need to assign the oxidation numbers to each of the following atoms in this compound. So let's just look one at a time at the different rules that apply to this. First of all, we can see that the sum of the oxidation numbers is 0. So when we find all the oxidation numbers together, they should total 0. What we do next then is we need to look at the electronegativities of silicon and bromine, and we look at the difference and see which is the largest. Since bromine has a larger electronegative number, we consider all the electrons as being belonging to it, and so we give it a charge of -1. Excuse me. So because in ionic compounds, all the electrons are seen as belonging to the compound with the highest EN value, Br has a -1 charge, and so it's going to have a -1 charge in this compound. So what we need to do then is we need to find what the charge is on silicon, or rather not the charge, the oxidation number. So we have 4 bromine atoms, that's 4 times -1, and silicon is going to be X, that's what it's going to stand for, and all of them together are going to equal 0, neutral charge. So X minus 4, because 4 times -1, equals 0. You can see then that X is going to equal plus 4. So each silicon atom is going to have a +4 oxidation number. So that one's fairly straightforward, right? Going on to this one here, we can see that again, it's going to have an overall 0 charge because it's a neutral compound. As we looked at earlier, usually H has a +1 charge, O has a -2 charge. So that's going to apply. So basically we have 1 H atom plus 1 Cl atom plus 4 O atoms gives an overall charge of 0. So we've got 1 H atom plus 1, 4 O atoms, each one of them -2, so 4 times -2. So we bring down this 1, we bring down this 4 times -2, which is 8. Chlorine atoms, what we don't know, we're going to put X for now. So we have 1 and -8 on the left side. That's going to give us -7. So we're going to have X minus 7. So X minus 7 is equal to 0. And you can see by looking at that simple equation that X must be 7. So each chlorine atom must be +7. So again, not too bad, right? The next question says, find the oxidation number of P in phosphoric acid. So to find phosphoric acid, you would need to look on the data sheet, which you'll be provided with, and the section you want to look at is relative strengths of acids and bases. Okay, so we find the formula for this from that sheet. Once again, we know that H is normally +1, so we have 3 times 1, or 3, for the H's. For the O's, we have 4 times -2, which is -8. We just put down P for the P's. We have 3 minus 8, or -5. So we have P minus 5 on the left side. We have 0 on the right. And again, you can see simple equation, P must equal 5. So the oxidation number for phosphorus is 5. Okay, switching gears a bit here, we're going to talk about voltaic cells. And voltaic cells are used in electric cars. As you can see, you have to have a lot of batteries in electric cars. It does kind of add to the weight of the electric cars, but you'll probably see a lot more electric cars, and hey, maybe someday you'll be driving one. So let's look a little bit more in depth at voltaic cells. Here's a diagram, and some of the most important things we want to notice here are that the anode is where oxidation occurs, and the cathode is where reduction occurs. Okay, so let's think of a way to remember that. If you think of the phrase, the red cat and ox, okay, so think of this picture, the red cat and ox. The red cat stands for reduction at the cathode, and ox stands for oxidation at the anode. Okay, so now that we have that in the back of our mind, we'll go back to the picture of the voltaic cell. So I added a minus to show that the anode has a minus charge, cathode has a plus charge. Now that specifically is for voltaic cells. There's other kind of cells where that's not the case. But let's think about why those charges make sense. Why is the anode negative? Well, here's what happens at the anode. You have zinc losing electrons and becoming zinc plus, Zn plus 2. The Zn plus 2 ions go into the solution, if there's a solution there. So because extra electrons are being produced, that's why it's negative at the anode. It also makes sense that the anode is negative and the cathode is positive because the electrons, which are negative, are traveling towards the cathode. So it makes sense that the cathode would be positive because negative charges travel towards the positive electrode. Okay, I think we've basically covered what's on this screen. So question for you here then. What reactions occur at the anode of a voltaic cell? Well, again, we remember the red cat and ox. So remember oxidation occurs at the anode and ox. Okay, so again, reduction at the cathode, oxidation at the anode. Now we're going to talk about a salt bridge, because a lot of voltaic cells have a salt bridge or something similar to that. Now what's the purpose of it? Well, if we look at the left side here at the anode, we can see that the Zn atoms are being changed into Zn plus 2. Now those Zn plus 2 ions are going to need to combine with SO4. They're continually being produced, but if they're going to continue to produce Zn SO4 to keep that concentration of that liquid constant, you're going to need to have some SO4 coming in from the salt bridge. Of course, SO4 is an anion, right? We have a cation being produced, and that's going to react with the anion and join together. So that's the purpose of the salt bridge, to provide anions for this side and cations for this side. Okay, so you can see the K plus is entering this side. So again, the salt bridge is a source of cations and anions, and to think of which electrode needs them from which salt bridge, or from the salt bridge, sorry, think of which ions are produced at that electrode, and then think of what type of ion will combine with the ions produced at that electrode. So for question 16, it says, what's the function of the salt bridge in a voltaic cell? Okay, so we know that oxidation occurs at the anode, and think about what oxidation looks like. You can write out an example of an oxidation reaction. That'll help you remember. Think about, okay, oxidation, that's losing electrons, becoming more positive. So since I have this positive electron that's going to be produced and sitting around in the solution that the electrode is sitting in other words, the electrolyte, I need an anion to combine with that. That anion has to come from the salt bridge. And again, the cation goes to the other side. So that's just kind of a way of helping you remember which type of ion goes in which side. Just remember, oxidation occurs at the anode, and so this is an example of an oxidation reaction. So again, because cations are produced, we need an anion from the salt bridge. That's kind of how the thought process goes there. So question number 17, which electrode do you think will increase in mass and which will decrease in a voltaic cell? Okay, well let's think this through. At the anode, what takes place? Well, of course, oxidation. And so the Zn atoms are being used to produce Zn plus 2. But those Zn plus 2 ions are leaving the electrode and entering the solution. So it makes sense that this electrode is going to decrease in its mass, doesn't it? Well, let's think about what's happening at the cathode. Well, at the cathode, we have this reaction going on. Cu plus 2 is going to Cu. So, basically, more copper is being produced. Well, what is this electrode made out of? You can see that it's made out of copper. So, in other words, this electrode is going to increase in its mass because more copper is being added to it all the time. All right. So making a voltaic cell, you have different possible candidates for making a voltaic cell as far as atoms and ions. But you can't just throw together any pair of atoms and ions. They won't necessarily produce a voltaic cell. So in order to find which pair of atom and ion will produce a voltaic cell, we need to know two things. We need to know the table of standard electrode potential. So that's a certain place on the data sheet, which we'll look at in just a sec. And we need to know this formula. Cell potential is equal to the cell potential at the cathode minus the cell potential at the anode. Now, once we subtract the cathode amount minus the anode, if we get a positive answer, then, excuse me, then the reaction will proceed spontaneously. In other words, we will get a voltaic cell. If our answer, when we do the subtraction, is negative, then we can't get a voltaic cell out of it. All right, so here's the table that we see in our data sheet, and we'll probably refer back to this in later problems. So this is page 51. Okay, so here's a question. Spontaneous redox reactions occur in voltaic cells. Which one of the following combinations could make a voltaic cell? Okay, so we've looked at the steps we need to carry out. We need to find the cell potential. We need to subtract cathode minus anode and see if we get a positive answer. If we do, then we get a spontaneous reaction. Okay, so let's look at A first of all. So if this is A, we get this reaction from the table, and the number we write down is 1.36. The number is 0 for this reaction. And now what we need to do is we need to figure out which one is the anode and which is the cathode. Well, it turns out that chlorine, the reaction where chlorine goes to 2Cl, that's oxidation. And the other one is oxidation as well. And since we have two oxidation reactions, we can't have any kind of cell potential there because we can't subtract the cathode from the anode. So this one doesn't work because for a voltaic cell to work, we need to have a cathode and an anode. So looking at the next one is B, and we find this reaction from the the standard reduction potential table. And so we write this answer down, we write the answer for the other one, and we get this. And then we need to again identify the cathode and the anode. Well, we can see that this here is reduction, right? It's becoming more negative, gaining electrons. This is the cathode then. Reduction occurs at the cathode. This one here, you can see we're losing electrons. This is oxidation. It's at the anode. So we do have a cathode and an anode. So we subtract cathode amount minus anode amount. Now, since it's minus a negative number, two minuses in a row give us a plus. So that becomes minus 0.41 plus 0.13, but our answer is still a negative number. So because it's still a negative number, we can't have a voltaic cell. So we look at C. So again, for C, we look at these, each one of these guys, these species, chemical species. We look on the table and we find this reaction and this reaction. We write down their cell potentials. Then we decide which is the cathode and the anode. Well, this one here, we can see it's gaining electrons. That's reduction, cathode. This one's losing electrons. That's oxidation. So we subtract the amount for the cathode reaction minus the anode reaction, and you can see we get a negative number. So again, no voltaic cell is possible. All right, last one. This is our last hope here. So again, we look at the chemical species. We write down the reactions from that table. We decide which is the cathode. Here we're gaining electrons. That's the cathode. Losing electrons, that's the anode. We do cathode amount minus anode amount. We have two negatives. That equals a positive. And so we get an overall positive number of 3.41. So this time a voltaic cell is possible using these two chemical species. All right, question 19. What is the cell potential of an electrolytic cell made up of Ca+2 and Cd? So what we need to do is we need to find, again, the half reactions. We determine which one is the cathode. This one's gaining electrons. It's the cathode. This one here, the way we write it, it looks like it's gaining electrons, right? But because Cd is reacting in this reaction, it should actually be Cd on the left side of the equation, so it would be the reverse. So in that case, oxidation is occurring at this electrode. Okay, so again we do cathode minus electrode. Because we have two negatives, that becomes a plus. We end up with an overall negative number here. So that is the cell potential. All right, question 20. It says a student attempts to make a voltaic cell from these two half reactions. Which of the following will be true? So first of all, what we need to do, some of these things are asking us whether a spontaneous reaction is going to occur. So if it is, we're going to have an overall positive number. So let's figure out which is reduction. That's going to be the first reaction because electrons are being gained. So this is happening at the cathode. Second reaction is oxidation at the anode. So we take this cell potential, subtract off this one, and so that's going to be 1.47 plus this number, and we end up with a positive number. So this reaction will occur spontaneously. Now, will chlorine gas be produced? Well, yes it will, because both reactions show chlorine gas as a product, so it will be produced. Well, will these concentrations of these two things decrease? Well, yes they will, because both of them are reactants. They're going to be used up, so their concentrations will be decreased as they're used up. The last thing is, will the pH decrease? Well, here's what we know. The more H+ ions we have, the more acidic it is. But H+ ions are being used up. So that means it's going to be less acidic. Okay? So it's going to be less acidic or more basic. So what does the pH look like when it's less acidic and more basic? The higher the pH, the more basic, right? Okay, so the pH is going to increase because it's becoming less acidic and more basic. Okay, so pH is going to increase rather than decrease. And again, the reason is the H+ ions are decreasing. And those are what make it more acidic. All right, now when you look at the periodic table, a lot of times you might think that those elements have been sitting there around for a long time. And in fact, they have been. A lot of those elements were created a long time ago. Just a few of them have been created more recently. Like in the last, I don't know, 30, 40 years, there was californium and einsteinium. Well, in 2011, there were two new elements that were added to the periodic table. I'm not even sure what they're called. And I'm just kind of curious, what would you guys call them if you were creating two new atomic elements? Anyways, the next question kind of relates to that. So it says we have a new metal that's been isolated, and it forms a soluble salt that looks like this. Now, a voltaic cell is made using the M rod. Okay, so just pretend that M stands for the name of the element. So that rod is dipped in this salt, and we also are going to have a standard half cell. So the cell generates this much voltage, and the hydrogen half cell is the anode. What is the cell potential at the cathode? Okay, so we have two reactions going on, as with other redox reactions. We're going to have this M reacting to form M+2, and we'll see why that is in just a moment. And we're also going to have the hydrogen half cell, and that we can find from looking at that table on the data sheet. So we see that this here is the hydrogen half cell, and we know that this is where oxidation happens because it says here that the hydrogen half cell is the anode. The anode is where oxidation happens. And we know that the potential given on that chart is 0 for this reaction. It's kind of unique that way. Okay, so how do we know that we're going from M to M+2 as far as the other reaction? Well, we know that if we had this solution here, this salt being produced, we know that NO3 has a -1 charge. We can get that from the data sheet, right? And so we know that M must have had a +2 charge, because these two ions reacting together will give us this salt. Okay, because we cross the 1 here and the 2 here, and that's how we get this as a salt. Okay, so that's how we know that this was M+2. So the reduction reaction at the anode would look like this. M+2 plus 2 electrons gives us M. Okay, so this is the cathode. And the question's asking us, what's the cell potential at the cathode? That's what we need to find. We know what the cell potential is at the anode, and we know what the overall cell potential is, and we use that info to find what the potential is at the cathode. So the formula for cell potential is cathode minus anode, so that overall amount is 1.24 volts. So here's what it looks like. Cell potential is cathode minus anode, and that cell potential we know is 1.24 volts. Cathode we need to find, anode is 0. So 1.24 is equal to some number minus 0. What's that number? 1.24. So 1.24 is also the cell potential at the cathode. Now another way of saying cell potential at cathode is reduction potential. That's just another way of saying the same thing. So if the question asks for reduction potential, you know it's at the cathode. All right, so we have a picture here that's pretty cool. It's a picture that shows electroplating. That's a process you can use to put a metal on top of another metal. So if you wanted to create a silver-plated spoon, you have a bunch of silver, and you could use this process to coat the spoon. All right, so this question kind of dovetails with this. Question 22 says we have 4 different cells, and they have different metals here. And it says they operate at 12 amps for 1 hour. It says at the end of this time, which cell will deposit the greatest mass of metal? So on page 515, it walks us through this process. It gives us another example, so you might want to look at that. But basically what we want to do is we want to find the number of moles of electrons. Once we find the moles of electrons, we can use that in the equation to find the moles of metal based on how many electrons there are, like based on how many moles of electrons are produced for each mole of metal. So we always find the moles of electrons the same way. We multiply the number of amps given by the time in seconds. So if it's 1 hour, that's 3,600 seconds. Then we divide by this amount. This is called a constant, this number. This number is found on your data sheet. Okay? So you multiply 12 times 3,600 and then subtract that amount by this here, number from the data sheet, and you're going to get this many moles of electrons. So again, we're going to relate that many moles of electrons to the number of each number of moles for each of the metals based on the equation. Okay, so when we write out the half reaction for copper, we can see that 2 moles of electrons reacts with 1 mole of copper. So in other words, we're going to get half as much copper as the number of moles of electrons. So if we had this many moles of electrons, half as much is this much copper. Okay, you can see for silver, it's going to be the same number of moles as the number of electrons. So this many moles of metal. Again, for this one, we're going to have half as much metal. So again, we divide by 2 and get this many moles of metal. For this one, it's a 3-to-1 ratio. Okay, 1 mole of metal to 3 moles of electrons. Get this many moles of gold. All right, now the question is saying which one is going to have the greatest mass. We found the number of moles of each metal. We need to change that into mass. But we need to look at the molar mass of each one of these metals. So from the periodic table, we see that copper has 63.55 grams per mole. So we multiply it by that many moles, and we get this many grams. We do the same thing for each one of the metals. So we get differing amounts of mass, and we can see that this one, for silver, is the highest amount of mass. Okay, question number 26. It says 46.5 grams of chlorine gas is reacted with this much silver to form silver chloride. Determine the mass of the oxidizing reagent that reacts. Oxidizing reagent is just another word for oxidizing agent. Okay, so we got to figure out which substance is the oxidizing agent, and we need to find its mass. So here's the reaction based on what we're told in this equation, or rather in the problem, the way it's described. So let's see which is the oxidizing agent. Well, when we go from chlorine to Cl minus, electrons are gained, that's reduction. We go from Ag to Ag plus 1, electrons are lost, it's oxidation. So Cl2 is reduced, so it's the oxidizing agent. So we need to find the mass of Cl2. Okay, how do we find the mass of Cl2? First, we need to have a balanced equation. So all we need to do is actually put a 2 in front of the Cl. So we have 2 Cl's on each side. Then we have to also put a 2 on this side. Now we have a balanced equation. Now we can find the mass of Cl2. So we're told in the question that 46.5 grams of chlorine gas is reacting. And we know the moles of Cl2 is this many, or rather the molar mass is this many grams per mole. So we find out that this many grams is 0.66 moles. We do the same thing for the silver, and we find out that we have this many moles of silver. Okay, this many moles of chlorine, this many moles of silver. Now, you'll notice that in the reaction, chlorine and silver react on a 1-to-2 basis. But it doesn't look like these two numbers are a 1-to-2 ratio. So one of them is in excess. We have too much of one substance. So when we look at these two numbers, 0.85 moles of silver and 0.66 moles of chlorine, we see chlorine is in excess, right? We should have half the amount of chlorine, but we have more than half. So we need to use the moles of silver to help us do the calculations. So, again, we focus on the moles of silver. We have 0.85 moles of silver, and we want to know how many moles that's going to produce of chlorine. Well, you can see that it's going to produce half as many moles of chlorine. So 0.85 divided by 2 is 0.43 moles of chlorine. We're almost there. We just need to find the mass of chlorine. So 1 mole is 70.9 grams. We multiply our 0.43 moles by that many grams, and we get 30.5 grams of chlorine gas. Okay, one thing that's important to remember is when we're using electrochemical reactions where we're applying a voltage to carry out a reaction, remember that the amount of time that it takes to carry out the reaction does not depend on the mass of the reactants you start with. Rather, it depends on the amount of voltage used in the reaction. Okay, we're getting pretty close, guys, to having completed this. This is a really important diagram because it can show you the ways that moles, volumes, and concentration, each one of those three things relate to each other. You might want to copy this. You might want to memorize it. Because what it's really telling us is that concentration is equal to the number of moles divided by the volume. That's what this means. Okay? Now, the number of moles is equal to the concentration times the volume. Okay, so you get how you can use this diagram to figure out those formulas? So we're going to have to use concentration in the next problem. So this question says, what's the volume of this concentration of silver ion necessary to react exactly with this many grams of zinc? Okay, well, let's look at the half reactions and let them help us to balance the equation. Well, we have Ag plus 1 electron goes to Ag solid. We have zinc goes to Zn plus 2 electrons. Now, things are not balanced because we have 2 electrons on this side and 1 electron on this side. So what we need to do is multiply everything by 2, and then we'll have a balanced equation. So we put a 2 in front of everything. Okay, so here you see this reaction with a 2 in front of everything. Now the number of atoms are balanced on each side, and the charge is balanced on each side. Okay, so from this equation we can see that 2 moles of silver ions react with 1 mole of zinc. Excuse me guys, I'll be back in a second. Sorry guys, things are just getting a little loud in the background with some squeaky toy that the dog was playing with. So anyways, so again, what this question is telling us is we need to find the volume of Ag plus 1 silver ion that reacts with this much zinc. So we need to know what the ratio is that these two things interact. And we can see that 2 moles of Ag plus 1 react with 1 mole of zinc. So if we find the number of moles of zinc that this is, then we can find the number of moles that we need here, and that'll help us find the volume that we need here using this concentration. So step 1, find the number of moles of this. Okay, so from the periodic table, it's 65.41 grams per mole. So we divide the mass we have by the mass of 1 mole, get this many moles of zinc. Since it reacts on a 2-to-1 basis, we're going to have twice as many moles of silver ion. All right, so now we're close. We have this many moles of silver ion. We need to find what the volume of silver ion is. So we use our formula, concentration equals moles divided by volume, to find volume. Now, if we wanted to find volume, again, we could use this little chart here. We can see that volume equals, okay, what do we want to find here? Volume equals moles divided by concentration. So we could do it that way, or, okay. And so another way of finding it, though, is since we know that concentration is always a certain number or a certain mass divided by volume, concentration is number of moles divided by volume. So we say concentration over 1 equals number of moles divided by volume. And now we still want to find volume. We cross multiply, so we say N times 1, or just N, equals V times C. If we want to find what V is, we can see V equals N divided by C. We divide both sides by C. So volume equals N over C. And again, we also could have found that from that little diagram with the triangle. Okay, so volume is equal to the number of moles divided by the concentration. So there's the number of moles we calculated. That's the concentration given in the question. And so we divide and we get this many liters. All right. Awesome. It looks like we are done. Okay, so again, please practice all these questions, all the blue questions from this whiteboard session on electrochemistry, which is done in 2 parts. Also remember for the midterm exam to go over the other whiteboard recording that we had for the first test and the study guide that goes with that. Again, the questions will be similar to these ones. So keep up the hard work, guys. If you have any questions about these, please give me a shout. And other than that, take care and have a great day. Bye for now.